Okay, in this video, I am going to review least squares regression, basically running a multiple regression model through STATA. And then in subsequent videos, I will review strategies for evaluating assumptions related to the model. So the data set for this particular set of examples um, I have already imported into the STATA program. I'm just going to show you really quickly. If you go to Data Editor, and then Browse, you'll see that I have a gender variable. It's actually coded 0 for male, 1 for female. So you're seeing the categories instead of the numerical values. Then we have subject matter interest, mastery goals, anxiety, and achievement, and then an ID variable for each case in the model, each case in the data set. We have 50 cases. We're just assuming that we have essentially 50 students with data on these variables right here. So after importing the data into STATA, you can see that over here we have the names of the variables. And what we're going to do is we'll start off just by running a basic simultaneous multiple regression. So in a simultaneous multiple regression, we basically add all predictors at the same time as predictors of variation in the dependent variables. So there are actually two ways that you can run the analysis. You can either use drop-down menus or you can use syntax. Knowing something about syntax is probably really helpful to kind of expedite things as you use the STATA program. But for this first set of examples, I thought I would just kind of walk you through both options. So using the drop-down menu, let's say I want to predict student achievement as a function of gender, subject matter interest, mastery goals, and anxiety. To run this analysis using the drop-down menus, I will go to Statistics, Linear Models and Related, and then go to Linear Regression. Okay, so this box is opened up and I will select achievement as my dependent variable, and my independent variables I will select gender, subject matter interest, mastery goals, and anxiety. Gender is already dummy coded, so like I said, a value of 0 on that variable represents males, 1 represents females. So we can interpret the regression coefficient for gender as reflecting a difference in the means for males and females, or means adjusted for the presence of the covariates in the model. So I'll click on OK, and so now you can see we get our basic regression output. And so you'll notice that we get the R-square value, which is basically the proportion of variation in the dependent variable accounted for by the predictors or the independent variables in the model. So that's 0.4585. So in other words, the predictors as a set, we're saying that they accounted for about roughly 46% of the variation in achievement. This is the F-test. It's a significance test. And we're basically testing the null hypothesis that the population R-square is equal to 0. So we're testing our data against that. So the alternative hypothesis is that the population R-square is greater than 0. So if we find that this is indicating statistical significance, then we're going to conclude or infer that the population R-square is greater than 0. So you'll notice that the p-value that is printed out right here is rounded off at 4 decimal places. There is no actual 0 p-value, so this is just reflecting the rounding. So it may actually be 0.00001 or something like that. So it's just rounded off. So typically in writing a research report, we would say p less than 0.001, something like that. Okay, so over here we get, we also have the adjusted R-square value, which is reflecting, well, as you can see, it's an adjustment to this R-square value for the number of predictors and the sample size. And basically what happens is that when you have a larger number of predictors and smaller samples, you end up running a greater risk of the model overfitting the data. So the R-square value can end up being somewhat inflated. So this is sort of a computational adjustment to the R square that we had originally. And that adjustment reflects, is basically an adjustment for the number of predictors and your sample size. Okay, so we also have the what basically amounts to the ANOVA summary table. So we have the sum of squares due to the regression, sum of squares due to the residual. The degrees of freedom due to the regression is 4 in this case because we have 4 predictors in the model. The degrees of freedom due to the residual is 45. So essentially that's just the total sample size minus 4, which is the number of predictors, minus 1. And then when we divide the sums of squares by their degrees of freedom, we get the mean squares. And so we get the mean square due to the regression, mean square due to the residual. And if we take a ratio of the mean square regression to the residual, we end up with this FA right here. Okay, so we also see we have our regression table, and you can see these are essentially the regression coefficients. We'll denote these with a little b for regression coefficients. This is the intercept for the model. So basically, oftentimes it will be denoted as b with a little subscript 0. And so that is essentially the predicted value on y, or the predicted score on achievement when the predictors are set to 0. So there you go. So that's essentially what this value is right here. So when the predictors are all 0, then the predicted value on achievement is 24. Then we have the regression coefficients for each of the predictors. So we've got a regression coefficient for gender. I'll just denote that as B subscript 1, subject matter interest, B subscript 2, B subscript 3 for mastery goals, and B subscript 4 for anxiety. And so essentially we want to test each of these for statistical significance. And so we do that by forming a ratio of the regression coefficient to their associated standard error, and that's what gets you the t-value right here. And then you'll notice that in this last column you've got the p-values associated with the test, and this is for a two-tailed test. So the null hypothesis regarding each of the regression coefficients, the null hypothesis is that the population regression coefficient is equal to 0, and I'm using beta right here to denote population coefficient. So we're using our sample regression coefficient as an estimator of the population coefficient. And so the null is that beta is equal to 0, and the alternative hypothesis really depends on whether you're testing a directional or non-directional hypothesis. So for a non-directional hypothesis, we would state that beta is not equal to 0. And for a non-directional hypothesis, we are going to be using a two-tailed t-test. So what that basically means is that if we start at the null, which is at the center of the sampling distribution under the null, where we would say beta is equal to 0, we would establish regions of rejection in the upper and lower tail. So when we set alpha, we're essentially setting a threshold within the sampling distribution under the null for rejecting the null and inferring that the population regression coefficient is not equal to 0. So typically or conventionally, alpha tends to be set at 0.05, and what we're trying to determine is whether the regression coefficient that we observe in our sample data deviates far enough from the null, in this case in either direction, to be able to reject the null and infer that that the population regression coefficient is not equal to 0. So that's for a two-tailed test, and basically a two-tailed test is used to test a non-directional hypothesis. So it doesn't matter whether the regression coefficient is greater than 0 or less than 0. We are just interested in determining if there's a significant difference from 0. Another possibility is that we could test using a directional hypothesis. So we might say, well, for an alternative hypothesis, the population regression coefficient is greater than 0, in which case, if we were drawing out our sampling distribution of t again, we'd be testing the upper tail of the sampling distribution. Or we might say that beta is less than 0, in which case we would be testing our hypothesis out in the lower tail of that distribution. So these p-values right here, these are basically for a two-tailed test. And so we're not, right now we're just going to focus mainly on adopting a non-directional hypothesis for each of these coefficients and just sticking with the two-tailed criterion. But if it's the case that you're testing a directional hypothesis, then the true p-value is actually going to be half of these values that are shown right here. So, or, if you have, let's say you've got a non-directional hypothesis for gender, but directional hypotheses for these right here, you'd be using a two-tailed criterion for the gender variable and one-tailed for each of those others. So, but like I said, we're just going to stick with the assumption that all of the hypotheses or alternative hypotheses are going to be non-directional. So we'll stick with the p-values as they are printed out right here. So we can see that using, adopting the alpha at 0.05 threshold, we would say then that that there is a significant difference between males and females on achievement. And given the coding, remember what I said, males were coded 0, females were coded 1. So this is the difference between males and females. The mean for males is actually going to be reflected in the intercept right here. And then the mean for females is just basically taking the intercept and adding the regression coefficient, and that would get you, roughly 27.9 for the mean for females. So the regression coefficient is reflecting the difference between males and females. If that coefficient had been negative, then that would mean basically that females would be scoring higher that males would be scoring higher than females. So at any rate, hopefully I didn't lose track there, but basically because this is a positive value, this would mean that females who were coded 1 scored higher than males, and like I said, if this was negative, then that would mean that that the females were scoring lower than males. So at any rate, there's a significant difference between males and females. And then when we look at subject matter interest, it's positive. So we would say for every 1 unit increase on subject matter interest, there was a predicted increase of 0.54 units on achievement. We see that predictor was also statistically significant in the model. And then when we look at mastery goals, we also see a positive predictive relationship, but it's not statistically significant. So this is non-significant. For anxiety, we see a negative relationship, meaning that as scores on anxiety are increasing, we see decreases on achievement. And we do see that variable is statistically significant in the model. So basically, it looks like that there's a significant gender difference favoring females, with females scoring higher than males. Subject matter interest is positively predictive of achievement. So in other words, the more interested you are in the material, the higher your achievement level tended to be. Anxiety was a significant negative predictor in the model. Basically, students who exhibited greater levels of anxiety also exhibited lower levels of achievement, and that variable was significant. And mastery goals was not significant in the model. So even though it was a positive predictive relationship, at least in terms of the regression coefficient, we see that it's not significant in the model. So basically then we would infer that really that the relationship that we're observing between the collective set of predictors and achievement in the model, that relationship is largely driven by gender, subject matter interest, and anxiety. Now, another thing to kind of note is that, you also see that there is a confidence interval right here, and the confidence intervals for each are formed around each of these coefficients. And so if you, so this is kind of providing sort of an interval estimate of the population regression coefficients. Just kind of keep in mind, too, that if you were using these to test statistical significance, the null was that the population regression coefficient is equal to 0. So that's the null hypothesis. So basically, if 0 falls between the lower and the upper bound of the confidence interval, of a given confidence interval, you would infer that a given regression coefficient was not statistically significant, as in the case with mastery goals. So you can see that 0 falls between the lower and the upper bound, whereas 0 falls outside of the lower and upper bound for the remaining predictors. And so consequently, we would infer that those predictors are significant. So if you're using the interval estimate to test hypotheses, obviously these results are going to mirror these results. So it only makes sense to report, the significance test if that's really what you're driving at. Okay, so if it's the case that you want the standardized regression coefficients, because they're not printed out right here. If you're in another program like SPSS, you'll get the standardized regression coefficients automatically, but here you have to ask for it. So here, if you go under reporting and click on standardized beta coefficients, you'll get the standardized regression coefficients, the beta coefficients. And so these are particularly useful in sort of rank ordering the predictors in terms of their relative contributions to the model. The downside of the unstandardized regression coefficients, which is what you have right here, is that they are scale dependent. And so it's really difficult to identify which predictors are kind of doing more of the work. So if you ask for the beta coefficients, then you can sort of rank order them in terms of their relative contribution. So if you just take the absolute values of these, then that will give you an idea about which predictors are doing more versus less of the work. So you see right here, you see that anxiety. Oh, excuse me. You have subject matter interest right here. The absolute value of these values right here, you see that subject matter interest has the largest beta coefficient, followed by anxiety, followed by gender, and then followed by mastery goals. And so that's kind of the sort of the rank ordering of the predictive contributions within the model. You'll notice that if you ask for the beta coefficient, so the confidence interval goes away. Now, you'll notice too that when running your analysis that if you run it through the menu option, you get the syntax associated with each analysis. And it's really probably very useful for you to kind of learn something about using the syntax. It's quicker than going through the menu options. So this is basically the syntax. It's already printed it out for you. And the way it's laid out is, it says regress, that's the command. Then you've got the name of the dependent variable and then the name of each of your predictors in the model. So I can use the command option down here to generate the same output and do it quicker. So I could type in regress, and then you've got the name of the dependent variable. Make sure that you are using the correct spellings, and also make sure that whatever is capped out, what letters are capped in caps over here appear in the same way down here. So we're going to type in achieve. We'll use gender, SMINT, and M goal, and anxiety. And so there you go. There's it's the same output as what we just generated above. If you want the beta coefficients, then we have to add a little subcommand. So I'll just type in regress, achieve, gender, SMINT, M goal, anxiety, and then comma, and then beta. And then that will generate the table with the beta coefficients. So that is sort of a quick and dirty overview of running the basic least squares regression model, basically the simultaneous multiple regression using STATA.